Hello. So today we're going to go over calculus graphing functions. We're going to use the calculus method and derivatives to graph functions. This is a quick review of how we can graph. We're going to find all the essential criteria to make our graphs as precise as possible. So the first thing I like to do is I like to find x and y intercepts. Now this is kind of like an algebra review. Okay, it's very much a review of algebra. So we have our x and y intercepts. What we do is we set, for our x-intercept, we set y equal to 0. We substitute a 0 in for y. So we have y equals mx plus b as a slope formula, or whatever it may be. Y equals, x squared plus 2x plus 1, whatever it may be, and so on and so forth. And then for our y-intercept, we'll set x as 0, fill in the x's as 0 instead, and basically solve for y on the other side. Okay, so if I were to give this if I were just to give an example, I'd have x squared plus 2x plus 1 over x plus 1. Okay, I'm going to solve for my, I'll solve for my x-intercepts first. I'll set, and this is equal to f of x, right? So I'm actually going to set f of x as equal to 0, x squared plus 2x plus 1 over x plus 1, okay? So I multiply x plus 1 over here, right? And that becomes 0, so I wind up getting 0 equals x squared plus 2x plus 1, okay? And now what I'm going to see is, okay, and then I get this equal to 0. So now what I'm going to do is I'm just going to factor, right? So I have x, if you've ever seen this x before, I like to do it this way. You have 1 and 2, 1 and 1 multiplies to 1, 1 plus 1 equals 2, so it's x plus 1 equals 0. Same, squared. You would say squared, you take the root of 0, you're going to get, obviously, still 0 equals x plus 1. Therefore, x equals negative 1. Okay, so it crosses at negative 1. So 0, you would say 0, comma, negative 1 is your x-intercept, right? Because x has to be 0 in that spot because it's intersecting that axis. Y has to be 0. Sorry about that. It'd be negative 1, 0. Y has to be 0 at that spot because we're intersecting the x-axis. If you picture the axis in your head, you would notice that if you picture an axis, x will be intersecting right here at negative 1, comma, 0. That's where our line will be coming through, right? So now if I solve for my y-coordinate, similarly, I'm going to plug in now 0 for x instead. So I'm going to take my original function that I wrote up over here. I'm going to plug in a 0 for my x instead. So I'm going to substitute 0 for x, right? So I wind up getting 0 squared plus 2 times 0 plus 1. 0 plus 1, okay? So I wind up getting, this is all 0, 1 over 1, which equals 1, right? Therefore, now I'm going to get 0, comma 1, right? Because x is going to be 0 at that spot, and it's intersecting at 1 for my y-intercept, okay? So those are my x and y-intercepts. That's the most basic spot to start at. Now we're going to move into asymptotes, okay? And you also have seen this in algebra. If you have done algebra before, if you take algebra, should have taken algebra before this, but if you have, you'll see now that the asymptotes, there's different rules for the asymptotes. We're going to go through them really quick. For a vertical, we always set the denominator equal to 0, right? So for a vertical, set denominator equal to 0, okay? So in this case, I had x plus 1 as my denominator. X plus 1 is equal to 0, therefore x is going to equal negative 1, okay? So in this case, you would say that we would have a vertical asymptote at negative 1, right? But there is one issue here. You cannot have a vertical asymptote here at negative 1. We can have a vertical asymptote, but the graph will be split in that spot, right? So when I go to find negative 1, when I go to second trace on my calculator and I put it in, I'm going to get a y. Y is not going to exist, see? Even though on the graph it shows that it passes through there, there's still a vertical asymptote there. There's a break. So I go to second trace on my calculator and I put in that negative 1. I clearly see that y doesn't have a value, whereas if I went to second trace and I put in, negative 2, I have a value. So basically, we are going to have an asymptote at negative 1, a vertical asymptote, okay? Now the next thing is, now we're going to solve for either a horizontal or a slant. Now in this case, this is our original function right here, okay? This is our original function. We have a higher degree over a smaller degree, right? And so what does that mean? That means we have a slant, okay? Normally, if we have x squared over x squared, we have the same degrees over one another. So I'm just going to write examples out. I have x squared over x squared. These two are the same, okay? We're just going to take the ratio of coefficients. And therefore, that is our horizontal asymptote. Okay? Now what we're going to do is, so for this, that's what we would do there, okay? Now, instead though, we don't have that situation here. We have a higher degree on the top than the bottom, so if this is higher than the bottom, than the denominator, then we have a slant asymptote, okay? And now, if the denominator is greater than the top, right, then we have y equals 0. And that's a horizontal asymptote, okay? But right now we're going to have a slant asymptote because it follows this rule where you have a larger degree over a smaller degree. So in this case, we're going to wind up saying x plus 1, and we're going to put this in the inside, okay? And basically what I want to do is I want to get this number right here by multiplying something in. So first I'm going to start with x. X times x gets me x squared, right? X times 1 gets me x, okay? So I'm going to say plus x. Now I'm going to distribute a negative into this whole entire thing. So now x squared goes away. I get a negative x, right? So 2x minus x gets me x, right? And then what I'm going to do is I'm going to bring down this 1 because I need to have 2 degrees, okay? And so if I look at this now, I'm just going to say plus 1, right? Because now it's 1 goes, right? It becomes x. 1 times x is x. 1 times 1 is 1. And then I make this negative, so now this all cancels. So there's no denominator, which is lovely. And even if we had it, there's no remainder. And even if we have a remainder, we wouldn't care about it because we just need to find the slope. So this is actually the slope of your line. Okay, this is the slope of your asymptote line. And so we see that here. We have x plus 1. So our rise over run is 1 over 1. And we see that it's plus 1. That's where it intersects the y-axis. And look at that. It intersects at 1. 0, 1, right? So that is our slant asymptote, okay? So we could label that as our slant asymptote is where it's the slope of a line, right? So it's going to follow this blue line. It's going to be like parallel to it, running right tangent with it, okay? So those are our asymptotes and those are our intercepts. Now the fun stuff comes into calculus. We found our asymptotes and intercepts. Now we're going to find our derivatives. We're going to take our first derivative or our second derivative to find our increasing, decreasing, our minimums and maximums, and our concave up and down, as where it's concave up and where it's concave down, as well as our inflection points where we're changing concavity. Okay, so if we look at this, we're going to take our first derivative. Okay, the first derivative determines our mins and max. Okay. We can find our mins and maxes. We could find our increasing and decreasing intervals. Okay, and that's about it. Okay, and these are our intervals. Okay, so we can find our mins and maxes, increasing and decreasing, and then we're going to use our second derivative to find our change in concavity. Right, or where it's concave up and down, basically. Okay, and we can find, where it's up and down, and we can also find points of inflections, right? Right, we can also find our points of inflections, where we're changing concavity. That is where we're changing concavity. That's our points of inflections. Okay, that's where we're going to find that. Okay, so that's what our first and second derivative does. That's all we have to really do for this. And then we could basically we could create our graphs, okay? So really quickly, I'm just going to walk through how we use our first and second derivatives, right? And then we could obviously graph, okay? We can make a graph. We could produce a graph that's very similar to the one we just produced on this TI-84 Plus, okay? Without even having to look at anything. We know our x and y intercepts, we'll know our asymptotes, and then we'll know where it's concave up and down. We'll also know where our points of inflection are, okay? And you can kind of tell, unfortunately, we had a sneak peek with this, but you can tell that there's no point of inflection because it's not changing concavity at all, is it? It's constantly increasing. It's a straight line. But if you had something more like a parabola or something more like a cubic function, you'll see that there's more of a change in concavity. In this case, we don't have that, okay, especially the cortex. So we're going to find our mins, maxes, increasing, and decreasing. Okay? Our mins, maxes, increasing, and decreasing. So we're going to take our first derivative, okay? Our first derivative is equal to, and we're going to use the same function, why not? So I'll have x squared plus 2x plus 1 over x plus 1, okay? To find our first derivative, we can use the quotient rule, or we can move x plus 1 up and make that, you can actually move this up and make this x plus 1 to the negative 1, right? And then solve using the multiplication rule. Whatever way you would like to do it, you can do it. I prefer using the quotient rule in this case just because I think it's a little easier to understand for me. But whatever you would like to do, it just makes it a little easier for me. So to use the quotient rule, I'm going to take the derivative of the top, leave the bottom as I see it, and then I'm going to subtract the derivative of the bottom, which is 1, times the top as I see it. Okay? Now I'm going to distribute this all out. So 2x times x, right, gets me, and I'm going to bring the denominator in at the end. So I'm going to put it all over the denominator squared. Okay, and I'll write it in, why not? So now what I'm going to do is I'm going to distribute all this out. So I'm going to wind up getting 2x squared, right, plus 2x minus, or plus 2x, sorry, plus 2, right, minus x squared. Notice I'm distributing this negative into everything because this is 1 times this. So minus x squared minus 2x minus 1. Okay, now things start to cancel here. So we got a negative 2x and a positive 2x canceling. And this is actually just going to become, we have negative x squared. So we're going to wind up getting just x squared, right, as we subtracted an x away, right, plus 2x, right, plus 1. When I find all my, when I combine all my like terms and simplify it out, over x plus 1 squared, right, it's over my denominator squared. All right, so we did this. Now what I'm going to do is, now you're going to say, okay, well now I got to find my critical values, okay, and I have to find my critical numbers. Okay, so my critical values, I'm going to set my derivative equal to 0, okay, so I'm going to set f of x prime equal to 0. So in this case, what I'm going to do is I'm going to set both the numerator and denominator individually equal to 0. So if I set the numerator equal to 0, we'll start with that. I'm going to have to factor, okay? And we did this earlier, I think. We got 1 and 1, right? So x equals negative 1, right? So that's one of my critical points. X equals negative 1. Now when I set my denominator equal to 0, we get x cannot be equal to negative 1, right? So, and that's because it's the vertical asymptote there, right? So even though in the numerator I got x plus 1, I set it equal to 0, right? Because I get x plus 1 squared equals 0. I take the root, and then I get x equals negative 1. X cannot, however, be equal to negative 1. So now I'm going to do what we do is we call this setting up our chart, okay? And I'm going to do this in a different color to help us out. Okay, so I'm going to set this chart, and what I'm going to see here is I'm going to set negative infinity. I'm going to set my intervals, right? Negative infinity to negative 1, okay? And then negative 1 to infinity. Okay, and that's about all I have to do because I only have one critical value here, okay? And then what I'm going to do is, I'm going to plug in values, right? So something that's less than negative 1, we could do negative 2. It could be anything, negative 3, negative 4, negative 5. And I'm going to plug in a value here as well, something greater than negative 1, which we could do 0. 0 is the easiest, okay? And we're going to plug that into my first derivative, notice. I'm going to plug it always into the first derivative. So I take my Texas Instruments 84 Plus or anything, any kind of calculator, scientific, and I go to plug negative 2 in. I'm going to plug it into my derivative note. So my derivative, my first derivative is really right here, right? So I'm going to plug this guy in. So when I plug it in, I'm going to wind up getting 4 plus 2 times negative 2, right, plus 1 divided by x plus 1. So it's really just negative 1 squared, which is positive 1, right? So it's really just 1, okay? And 1 is a positive number, right? So since it's positive, the function is increasing, okay? Now I'm going to plug in 0. I plug 0 into these, I get 0. I get 1 over 1, which is equal to 1. Therefore, it's increasing as well. And it makes sense because when I looked at my graph, it's constantly increasing. It never decreases, right? So in this case, it's increasing from negative infinity to infinity. You could write it just like this. Negative infinity to infinity. And decreasing, it's just not decreasing. You can write none or not applicable, whatever you want to write. It's not decreasing at all, okay? It only increases from negative infinity to infinity. We don't have to write... Oh, actually, I'm sorry. We have to write that we have a vertical asymptote. That's right. So this is the trick problem. This is the main thing that we make a mistake on. We say that it's increasing. We could say that it's increasing from negative infinity to infinity, but there's a break because there's a vertical asymptote. So you really have to say that it's increasing from negative infinity to negative 1, and then negative 1 to infinity. Okay? That's my domain. This is also my domain here, right? Right? It's also the same as my domain because it's increasing from negative infinity to 1 and it's stopping at an asymptote, and then negative 1 to infinity. A lot of misconceptions is that people say it goes from negative infinity to infinity, and it does. It truly does go from negative infinity to infinity. But in this case, it's actually going to have a break at that vertical asymptote, okay? Okay, and now for my relative minimums and maximums, okay? So I have a relative. Now notice how I put an R in front for relative, because these are relative. They're not absolutes, okay? They're relative mins and maxes. They could absolutely be a relative. They could actually be the minimum and maximum, the absolute. But we don't know for sure because we didn't test all of our values. But so we call them a relative min or max, okay? So we have a min and a max, okay? Where it's increasing and where it's increasing is always our mins and our maxes, okay? Now, the funny thing you're going to notice here is I'm always going to plug in these x values into the originals. That's my x value and that's my x value. Okay, so right away, if it's increasing, right, if it's increasing, it means it's at a low point, which means that we have a minimum. All right, so that means we're never going to have a maximum here, so you can get rid of maximum. So clearly we don't have a maximum because our points, we're starting, we're going to plug in. Nowhere is it decreasing. So that means, right, if it's decreasing, we're going to have a maximum because it's at a high point. Just picture it in your head. We have this graph, okay? It goes like this, okay? If we're at a top point, it's going to be, if it's increasing at a point, then this is a minimum, right? And if it's decreasing at a point, then that's a maximum, okay? We see the difference here. So if it's increasing, it's a minimum. If it's starting to decrease, it's a maximum. So in this case, we're increasing. So we're going to actually have a minimum. However, are we going to have a minimum? So I plug in negative 1 in, which is my x value, into my original function. Am I actually going to get a good answer? And the answer is no. There's no relative minimums and maximums here because look what happens. If I plug a negative 1 in right here for x and my denominator, I'm going to get 0. And I can't have a zero-case denominator because it just doesn't exist, right? So therefore, there's no relative mins and maxes. You can write none, okay? So that's just a way of knowing what to do conceptually, okay? It can get confusing at times. So now what we're going to do is we're going to go through concavity, okay? So concavity requires us to take the second derivative, and this is where it can get a little funky sometimes. So we have this part here. This is our first derivative. We'll write this down right here, okay? So we have x squared. We'll write this to refer to over x plus 1 squared. When we take our second derivative, we can either do the quotient rule or we could do the product rule. It can get confusing now because if we do the product rule, we could bring this guy up to the top, but it can get confusing because then you got to do you got to do the product rule and then the chain rule at the same time in order to find the derivative of that, and that's where it gets a little funky. I like to do the quotient rule, but a lot of people like to do the product rule just because it's a little bit easier and it gets harder at these higher order derivatives, okay? So when I do the product rule here, I'm actually going to if I do the quotient rule here, I'm going to take the derivative of the first. So the second derivative is going to be a derivative of the first, right, plus 2 times the bottom as we see it. And now we could FOIL this out, right? So if I have x plus 1 times x plus 1, I'm going to wind up getting x squared plus x plus 1. Right, so I'm going to get x squared plus 2x plus 1. It's just easier to FOIL it out now. And then I'm going to subtract the derivative of the denominator. Right, so now I take the derivative denominator. I could take the derivative using the chain rule, or I could do it now the way I did it. So I could do 2x plus 2 over x squared plus 2x plus 1, okay? And so I'm going to distribute this guy out to the whole thing after I FOIL all this out. But this is where it gets crazy because we're going to have to FOIL out a lot of stuff here. And then we have x plus 1. We have this over the denominator squared. So the denominator squared is now going to go to the fourth, right, instead. So now what's going to happen is I'm going to FOIL all this out. And this is where it gets very, very crazy. Because I'm just going to write equals here. I'm going to get 2x. I'm going to multiply the first guy out. So I'm going to get 2x to the third, right, plus 4x squared, right, plus 2x, okay? Now plus 2x squared plus 4x plus 2 as I go across, right? Now I'm going to get minus 2x to the third, right, plus 4x squared, right, plus 2x, right, plus 2x squared plus 4x plus 2. Okay, now this is kind of crazy here. And then we're going to get all this over x plus 1 to the 4. Okay, now we just have to cancel our values out. So if I distribute a negative value into this goes away. I distribute a negative into this goes away. A lot of canceling here. I distribute a negative into that guy goes away. I distribute a negative into that guy goes away. All right? And it just keeps going. This guy and this guy, right? And so what we wind up getting here is we wind up getting negative 2. But look, I get down to this. I get 0 over x plus 1 to the fourth, which equals 0. So the second derivative is 0. And guess what? I look at my graph and it actually makes sense. There's no concavity here. It's just a straight line. I picked a straight line equation. So guess what? There's no points of concavity. However, if there were points of inflection. However, if there was concavity here, what I would wind up doing is I would take my values from this. I would take all these critical values after setting them equal to 0, right? I would take my critical numbers from this, okay? And I'd plug them into, I would do the same thing with my chart. I'd do negative infinity to that critical number, and then that critical number to positive infinity. And I could, I could add whatever in between. Well, I could add them in between, actually, not at the end. The numbers that, any other numbers that I would have in between negative infinity, and I'd test into the, I would test the number into the second derivative. The second, not the first, notice. Okay? If it's a positive number, it's concave up. If it's a negative number, it's concave down. Okay? So this is how we determine this. Okay? And then points of inflection, I would take my x value. This is the only, because I can't plug infinity in. I would take my x value from my point. This is a possible point of inflection, unless there's an asymptote. Okay? So if this were to really exist, I would say that I would plug this into my original function, but if there were an asymptote there, like there is -1, that actually you wouldn't be able to do it in an asymptote because there's no point of inflection at an asymptote note, okay? So this is just a quick review of how to do graphing. This is how you would graph, and then you would go in and actually, graph your algebraic function in this case. And you would wind up getting something very similar to this. You would get a straight line, which makes sense because you'd have your slant asymptote and you would count your slope out. And you have your x and y intercepts. Sorry for the blurriness. You'd have your x and y intercepts. One's at 0, 1 for your y-intercept, and your x-intercept's at -1, 0, okay? So you'd plot those 2 points. You would draw your straight line. You would have an asymptote right here, note, and then you'd be done for the day, okay? So thank you for watching. Please leave comments if there's any other questions. Thank you.